Now let's take a step back and quickly have a look at the classical picture. And we're going to review Hamiltonian mechanics, but from a different perspective than what we've looked at in our previous courses in classical mechanics. Let's consider a very simple example of a particle in one dimension. Now, if I know the position, the velocity, and the time at which I captured these, then I'll know the state of the particle. We define the phase space as the space of all possible states of a system. Now, in our simple example, we will have a time axis, a position axis, and a velocity axis. And any point phi in the space will represent the state of the system. Now, an interesting phase space in Hamiltonian mechanics that's commonly used for any system is a phase space that contains the generalized position, generalized momentum, and time. If you're unfamiliar with the concept of generalized coordinates, then you can consider these to just be position and momentum. Now, we discuss observables in quantum mechanics, and they roughly correspond to real values that can be measured and are obtained using Hermitian operators. Analogous to that, we can describe observables in classical systems using some smooth function f that maps my phase space to a real number. So that's my phase space, and that's what I observe. F is smooth because in our phase space we have position and momentum, which are smooth dynamical variables. For example, the position function qi that selects the ith component of the position vector. Similarly, the momentum function picks out the ith component of the momentum vector. Now, something you probably haven't heard before is that every smooth function over the phase space is associated to a vector field over that phase space. The math of how we get this involves topics that are beyond the scope of this course, so we will consider this to be given. Now, consider a smooth function f, then the associated Hamiltonian vector field xf is given by the partial derivative of f with respect to the momentum coordinate and the negative of partial derivative of f with respect to the position coordinate. Remember that this field is over the phase space. Let's take an example of the momentum function. The associated Hamiltonian vector field will be given by another important point that the vector field will have an associated flow in the phase space. Let's visualize this. Now, I've plotted the momentum function in the PI/QI phase space. The black arrows indicate the Hamiltonian vector field, and the orange arrows indicate the flow of the vector field. Now, let's say that I pick a state in this phase space, and it has position q0 and momentum p0. Now, if this state follows the flow, is then translated in position. Now that this is a uniform vector field, so any state will translate at the same rate. What does this mean? It means that the flow generated by the momentum function causes position translation of the state in the phase space. Hence, we call the momentum function the generator of position translations in the phase space. Now, we know what generators mean in Hamiltonian mechanics. These generate flows in the phase space that causes a state, which is an element of the phase space, to translate in coordinates. We'll look at two more examples to solidify our understanding. The first is the position function. Now, you can see that any state in the flow generated by the position function will translate in momentum. And note that the momentum coordinate here will decrease. So from our definition, we can say that negative qi is the generator of the momentum translations in phase space. Note that the negative here is taken due to the convention that generators translate states such that the coordinates increase. Now let's look at our final example of the total energy function, or Hamiltonian. For simplicity, let's take an example of free particles. So a free particle will only have kinetic energy, which is given by p squared over 2m. When you take the derivative and compute the Hamiltonian vector field, you'll find that the flow is given by the velocity of the particle in time. Now let's analyze the plot. We can see that the vector field is no longer constant and the flow depends on the value of momentum, which means that if I pick two states starting with the same initial position but different momentum, the one with a higher momentum will flow faster than the one with the lower momentum. Now take a moment to pause and think about this. This flow exactly represents the flow of our state in time. Now let's understand this. Say our particle starts with some velocity v0. We know that since this is a free particle, there are no forces in our system, hence the velocity will not change. So if our particle starts with position q0, the position of our particle will be the initial position plus the velocity times t. v0 is the rate at which my particle flows in time, which is exactly the flow generated by the Hamiltonian vector field. That is, the flow or the size of these arrows indicate the velocity of the particle in time, and thus this vector field essentially represents the time evolution of a state. So if I start with any state, its evolution in time will be exactly described by this flow. Hamiltonian generates a flow that translates a state in time, or evolves the state in time. Hence, Hamiltonian is called the generator of time translation or evolution.